In March 2018, we embarked on a research project that sought to establish the most cost-effective method of manufacture for a nuclear waste container. At every point on this journey, the solutions realized were predicated by the unavoidable and intrinsic fact that vibration is the enemy of machining. Given the nature of the material, a duplex stainless steel, and the properties of the part itself, every conceivable source of vibration has been considered, from the machine bed to the column, the guideways themselves, the spindle tool interface, the cutting tools used, their grade, their geometry, and a forensic analysis of how the part itself is being held. Doing the maths and working within the laws of physics dictated the direction taken. And this video book seeks to depict that journey. A journey that culminated in successful cutting trials undertaken in Coburg in Germany late last year and early this year, and the issuing of an important industrial patent. Tap testing, or modal testing, is a non-destructive process commonly used within industry where limiting vibration is an essential part of protecting the integrity of a part or a structure. It can be used across a broad spectrum. From some machine tools would use it, aerospace components, the chassis of a motor car, even civil structures like bridges. It is resonance that we're interested in, as this is the real killer. It can lead to the amplification of vibration and ultimately the destruction of structures themselves. The wind effect on the Tacoma Narrows Bridge is a classic example of how resonance can do its damage. When it comes to machining, any resonance that occurs due to poor fixturing or the lack of structural stiffness in the machine itself leads to chatter and inaccuracies. Chatter reduces tool life as the cutting inserts are not machining at a constant force or depth, which inevitably leads to a deterioration in productivity. To understand the natural frequencies of the MSSS box, it was examined in 3 different conditions, each referred to as a degree of freedom. In each of these 3 states, modal analysis was conducted in 12 different but repeatable locations around the fabrication. The first set of tests were completed with the box in a free state, resting on 3 stands, representative of how it would sit within the fixture. This was done to get a clear idea of the box's inherent resonant frequency before any external influence has been applied. The second set of tests were completed with the box hydraulically clamped in the fixture. This meant that all 32 touch clamps, 3 push clamps, and 12 swing clamps were engaged. These tests were completed to give an idea of how much vibration there would be within the part if only conventional clamping processes were employed. The third set of tests were completed with the box hydraulically clamped, as in step 2, but with all external and internal airbags engaged also. The following tables show the time taken for each of the inputs to reach a point where the amplitude remained below 0.1 G. The overall reduction in time for the assembly to return to a steady state, i.e. below 0.1 G, was up to 150 times quicker with all clamping features engaged, with an average time of less than 0.02 of a second measured. The high degree of dampening limits the build-up of vibrations during the machining process. When considering the action of milling, each individual tool tip represents a strike. Closer analysis of the feeds and speeds of one of the tool paths clearly explains the benefits that the dampening effect induces. If we imagine a cutter that is rotating at a speed of 176 RPM that contains 8 individual cutting teeth, the maths is relatively simple to work out. 176 times 8 divided by 60 gives me the number of taps per second, in this case 23.466 taps per second. If I work that out in terms of time, that's 1 second divided by 23.466, equates to a gap in the strikes of 4/100ths of a second. In this case, when looking at the dampening properties, the agitation induced in the material through the cutting process has completely dissipated in the elapsed time between the striking of the first and second tooth. An outcome that is impossible to achieve under conventional clamping conditions.
Around the front of the fixture you've got 12 swing clamps. These swing clamps are located and connected to the machine, so as the cutter moves around the front of the machine, the swing clamps move into position and move out of position. So at any machining time you've got 11 clamps in contact with the job. And with the combination of the vibration suppression of the airbags, the job stays very rigid and stays in the same place. You can see a big steel plate that's sitting inside of the box. Behind that are 5 airbags, one round each face and one at the back. In the fixture itself, there's also 5 airbags, again 4 around the outside of the box and 1 at the back. We've used the airbags, both internal and external, to apply an opposite and equal force, which reduces the vibration in the 6mm walls.
The combination of the superbly configured Taurus 30 from Valdric Coburg and a fixture design that alters the resonant frequency to such an extent that it has similar properties to a solid cube of metal eliminates the need for compromise in the machining process. Listen to the actual sound recordings of the various cutting processes. Evidence of processes that are in complete control.